you about how you can set up your particle counter to avoid false alarms, and at the same time, you can set up your alert and your action levels. I'm going to be using a parametric method. Although this is written in Python, we don't need to explain any of the code. We won't be focusing on that. We're just going to focus on just the technique. So I'm going to explore this parametric method, and I'm going to use these reference points to explain the technique. So here are my references, and I'm going to go through them very quickly right now. So um, particle counters, particles entering the clean room follow the Poisson distribution. If you look here inside of 21501-4 at Annex C, you'll see that the probability of false particle counts is written here. They specifically express that it is the Poisson distribution that's being used. Now, to get alert and action levels, this paper probably explains at best the application of the Poisson distribution in establishing control limits for discrete quality attributes. The authors did a really great job of explaining how to use the Poisson distribution to establish your upper and lower alert and action limits. And the technique is for the action limits is actually expressed here in this PDA journal, which is the determination of the action and alert based on historical data. So both papers talk about how you simply gather historical data, get the average, and then once you have the average, you multiply the average by 3 times the standard deviation. Now, what's interesting is standard deviation in the Poisson distribution is just the square root of the mean. So that makes our job a lot easier. We can now maybe go to table 5 in EU Annex 1, and we notice that for the 5 micron, you can have as many as 29 particles. Well, even though I haven't collected any samples, we can create a scenario out of this. And we can say that our control limit is 29 particles, and we're going to say that that's equal to the mean plus 3 times the standard deviation. But what's the mean and the standard deviation? Well, because of the Poisson distribution, we know that the mean and the standard deviation is the square root of the mean, right? That's the magic behind the Poisson. So we can rearrange the equation, and then we can use the quadratic to solve for the mean. And then once we get that, we can also solve for the alert limits. And this is what the math works out to be. The mean is 16.73, and then the alert limit is 24.91. This is just the math. Remember, when you use the quadratic, you actually get uh, uh, two answers. The reason you throw the negative answer out is because it's negative and there's no such thing as negative variance. You can only have positive variance. So let's just go ahead and plot that distribution out so we see how that looks when we plot it. And you have a mean of 16.73. You have the action level of 29, the alert level of 24.91. Pretty easy. So, and you can see that this is the mean at 16.73. These are exactly, this is 2 standard deviations from the mean, and this is approximately 3 standard deviations from the mean. So, that's the width of your process. But the problem is that in table 5, they're not expressing anything more than a concentration. So 29 particles means it's 29 particles that you can have in 1 cubic meter, which is the same as 29 particles inside of your 36 minutes, or you can look at it in liters, 1,000 liters, or 35.31 cubic feet. So that's the concentration. Well, if there is a concentration, that means that in 1 minute, or in 1 cubic foot, or in 28.3 liters, however you want to look at it, there's a concentration of particles that's allowable. Okay. And then you're going to be in an alarm. So how would you look at that? Well, that means that you can only have 0.81 particles per minute. The problem is that it is the Poisson distribution, and particles are discrete quantities. You can't have half a particle, can't have 8/10 of a particle. So how do we set our alarm? Well, unfortunately, your particle counter will be set to an integer. You're going to be set to 1. And this is going to put you at an extremely high risk of going into alarms every single time you turn your particle counter on. And then the question is, do you respond to that alarm or do you just ignore it? Maybe ignore it could have major consequences. I mean, you have to justify it later on. And response could also have major consequences. So it puts you in a bind. Well, we can go back to Annex C on 21501-4, and we know that there is a probability that you're going to get a false count on that first minute, right? And we can actually estimate what that is. So I said, well, what's the probability you're going to get false count on that first minute? Turns out to be it's about 29%. I'll take you to the math in just a second. But my next question is, if what is the probability that you get three consecutive false counts in a row, right? The one reason I picked three was because that's just, one of the basic rules of thumb for a trend, three consecutive events in a row. So what is the probability? Well, let's put this into Poisson distribution. Again, we just use lambda as the mean, we use k as the number of particles, and we use Euler's number, and we just expressed it as following. So 29% for minute one, but by the time you get to minute three, it's 2.4%. That means it's a dramatic fall. It means the probability of you having three consecutive events in a row is incredibly small. It's only 2.4%. So what does all that mean? Well, a couple of things. First, it means that a bad strategy for setting your alert and your action level, like for example, you want to set uh, your alert level to 24 particles. That may be too late. You may be experiencing a particle event and then you did not witness or identify it. But it would be nice if your particle counter has an alarm that could say, hey, we have 24 particles. That's a problem, or we're getting there. That would be a great alarm to have. But a second alarm that you should have is one that says, hey, if I get three in a row, then we are having a particle event. Three particles in a row, then we're actually having a particle event. And that would be nice to have also. So there would be two ways that you could set the alarms for your particle counters. Now, in conclusion, you want to set your alert for your action and your alert levels. We showed a little bit about how that math works, or how you could do that by collecting samples and getting a mean and following the math. But in order to ignore your false alarms, the suggestion is that you have these three consecutive events, and only on the third event do you get an alert from the particle counter. And that should solve the problem. But there may be more techniques, because keep in mind that after the first 36 minutes, those three consecutive events may be less significant.